So in last video we discussed about viscosity. We saw that whenever you have the layers of liquid, the liquid is flowing, then between two layers you may have a viscous force which tries to oppose any kind of relative motion between the two liquid layers. Here in Poiseuille law we will consider the flow of liquid in a capillary tube. Suppose we have a capillary tube like this and liquid is flowing in this capillary tube. Suppose liquid is flowing in this capillary tube. So the liquids are flowing in a capillary tube. So the surface of the tube, the outer surface of the tube, is stationary. So the layer of liquid which is sticking to the outer surface will remain stationary. The layers of liquid, and the layers of liquid will be of what kind? It will be some kind of cylindrical layer of liquids. Since the tube is cylindrical, so layers of liquid will be of cylindrical shape. Into all these things we will discuss. So these layers flowing inside. One more. Okay. So fine. So these layers, the layer of liquid will be of this kind of shape. There are cylindrical layer of liquids. Similarly on this side also they are the layers of liquid which are flowing. So the layer which is just near this surface of the tube will remain stationary. Velocity of this layer is going to be 0. And as you go towards the axis, suppose I say this is axis, suppose say this is the one, let me take the red one. Suppose this is the axis. So the layer of liquid which is near this surface of tube will be stationary, and as you move in this direction the velocity of the liquid layers will become faster and faster, and at this point the velocity will be highest. The velocity of layer which is near the axis will be highest, and velocity of the layer which is attached to, which is sticking to the surface of the tube will be 0. So velocity keeps on increasing as you move towards the axis from the surface. As you move in this direction, velocity keeps on increasing. Since there is a difference in velocity between two layers, so if you have a viscosity, if suppose this is a viscous fluid, you may have a non-viscous fluid also. If it is non-viscous, then there is nothing in it. If it is viscous liquid, then since there is a difference in the velocity of the layers, then in that case there will be viscous force acting on these layers. There will be viscous force acting on these layers, and if you want the velocity, or if you want the flow to be steady, if you want that velocity at different point in the fluid does not change with time, velocity will change in space, but if you wish that because of this viscous force the velocity at different points in the fluid does not change with time, in that case you have to apply pressure. You have to apply pressure from this side, so that this pressure will overcome any viscous force which is acting on the fluids. If you want that velocity should not change with time, velocity can change in space. Velocity at this point is 0, velocity at this point is highest, but I want that these velocities should change in space, but this velocity at any point in space should not be a function of time. In that case you must overcome this viscous force acting on each layer by applying pressure from outside in the direction of flow. By applying pressure from outside in the direction of flow. Alright, so to have a good analysis, let us consider a cylinder over here. Consider the liquid lying in this cylinder. Consider the liquid which is lying in the cylinder, right? Since the layer just above the cylindrical surface will be having lower velocity, this layer will have a lower velocity compared to this layer. So these layers will exert a viscous force in this direction. Viscous force in direction opposite to the flow. The liquid is flowing in this direction. Then the layer which is outside the cylinder, which is just outside the cylinder, they are going to exert a viscous force on this liquid. We have considered this volume liquid which is bounded by a cylindrical surface, imaginary cylindrical surface. So the velocity of these layers will be higher compared to these layers. So these layers are going to apply a viscous force in direction opposite to the motion and hence opposing relative motion. So what are these forces? These forces are in A dV by dx, and suppose radius of this is x. So this is n into area would be how much? Area is area of this curved surface area of the cylinder, 2 pi x dV by dx. And if we want the flow to be steady, when do you call the flow to be steady? When physical quantity associated with the flow is not a function of time, and the physical quantity we are interested in over here is velocity. When velocity can be a function of space, but it's not a velocity is not a function of time. If I don't do anything, then this viscous force will lead to fall in velocity of these layers. But if I want that the velocity should not change with time, in that case, in order to overcome this viscous force, I must apply a force from outside. So suppose I apply a pressure P from outside, then this pressure P will translate into force on this liquid, and that force will be P into pi x square. So this will be dV by dx. And one more thing, since this V is falling as x increases, this V is falling as x increases, x is measured from the axis. As x increases, V is falling, so dV by dt is inherently a negative quantity. See, if I want that this side and this side should have a same sign, then I must put minus sign over here, or I should put minus sign on this side, right? Then only this equation will hold good, because this side is positive and this dV by dx is inherently a negative quantity, because V is increasing as you increase x. As you go towards increasing x, V is falling. V is falling, so dV by dx is inherently a negative quantity. So if you want to equate these two, you must put minus sign over here, then only it will become positive. So positive and positive can be equated, positive and negative cannot be equated. So dV by dx is how much? dV by dx is P upon minus P upon 2 neta, and this area is not 2 pi x, area will be 2 pi x into L. If suppose L is the length, 2 pi xl, so P upon 2 neta L x. So dV would be P upon 2 neta L x dx integral. At when x is 0, suppose velocity is v, and when x is r, or we know the velocity at x equal to r, we know the velocity at x equal to r, velocity at x equal to r is say 0 when x becomes equals to r is the radius of cross section, the velocity is 0, and when x is x, the velocity is v. When x is x, velocity is v. So we can say v equals to P upon 2 neta L x square by 2 minus sine r to x, or this is P upon 4 L r square minus x square. This is how the velocity is going to. So this equation is giving you how the velocity changes as one moves along across the cross section. As one moves across the cross section. Suppose I take this cross section, so this cross section, and I keep on plotting the velocity. Velocity over here is 0. The velocity over here will be somewhat more than 0, and as you go towards the axis, velocity keeps on increasing. From this, see, as you go towards the axis, x keeps on falling and velocity keeps on increasing, and it reaches the highest when it goes to go to the axis. At the axis, near the axis, the velocity of layer is highest, and as you go below axis, the velocity keeps on falling. So if you join these points, tip of this velocity vector, you'll find that you get somewhat like parabola. You get something like parabola over here, and that's quite obvious from this mathematical equation. This is equation of parabola in the variables v and x. If I take variable v and x, this is the equation of parabola. So it is parabolic kind of thing. Velocity is 0, keeps on increasing as you go towards the axis, and then keeps on falling as you move along this cross section. Velocity keeps on increasing, then from here it is maximum, and then keeps on falling and goes to 0 again. So this is how velocity varies from one layer to the other layer as one move along across the cross section, right? So this is the variation of velocity at different point of the cross section. You want the velocity at any point of the cross section, you just put the value of x. You want velocity at this point P, just see this, what is x over here, put this over here, you get the velocity at this point. So this formula gives you velocity of fluid at different points on the cross section, or it gives you velocity of different layers. If you want a velocity of particular layer, you just see the radius x, put it over here, you will get the velocity. Now a very important thing over here is how much volume of liquid is flowing per second through this capillary tube. We are interested in finding out volume of liquid flowing through the tube per second. Remember, P is the pressure which we apply from outside to overcome this viscous forces. So we are interested in finding out volume of the fluid flowing across the tube per second. Suppose I take you want to find velocity of the fluid flowing across the tube per second. See, velocity at different point is different. If velocity could have been same, what could I have done is I would have just multiplied A into V. That could have given me volume of the liquid flowing per second. But since V is not constant over whole cross section, we can't use this. But we can definitely take an element of the cross section. We can definitely take an element over the cross section. Let me use black pen over here. We can take an element over the cross section, element of radius x, and thickness dx. Element of radius x and thickness dx. And let's find out the velocity of the volume of the fluid flowing through this cross section. Let's find out velocity of the fluid flowing through this cross section of radius x and thickness dx. Right? So the cross section area is how much? 2 pi x dx, and volume of the fluid flowing will be cross section into velocity v. So that will give me the velocity, that will give me the volume of the fluid flowing through a cross section of radius x and thickness dx. Cross section in the form of ring of radius x and thickness dx, that will be this. So total fluid which is flowing through this tube would be integral of this 2 pi x v dx, or this will be 2 pi x and V at a distance x from the axis is given by this dx. All this will be pi p 2 neta L, these 2 will cancel out, and integral of we have x also, so x minus x cube dx from 0 to capital R, 0 to small r, I is the radius of cross section. So pi p 2 neta L, and this will be x square by 2 0 to r, and this is pi p 2 neta L r4 by 2 minus, so that is r4 by 4 8 neta L. So volume of the fluid, volume of the liquid flowing per second through the tube is pi p r4 by 8 neta L, this, right? And this is the Poiseuille formula. This is the Poiseuille formula, right? You can also express, you can from the here you can get neta also, that will be q 8q neta will be what, pi p r4 upon 8ql, right? So from here you can understand that if you increase the radius of a tube twice, if you make the radius of the capillary tube twice, the volume of the fluid coming out will become 16 times. 16 times. So it's easier, if you want to get more volume of the fluid coming out, then you should increase the radius. If the radius is increased, it becomes 4 power. If R becomes 2R, then Q becomes 16Q. Q increases 16 times. Q to the power 4 is 16. Okay, so this way you can see this. So this is what is Poiseuille formula. Okay, I'll stop over here. Thank you.